In the previous episode, we explored the heart of modern artificial intelligence, the GPU. These processors perform the enormous number of calculations that are required to train and run AI models. But raw compute power alone is not enough. A GPU can only perform calculations if it has constant access to data. And modern AI models require an enormous amount of data movement. Weights, activations, gradients, and training datasets must constantly flow between memory and the processor. If this cannot be delivered fast enough, the GPU simply waits. In other words, the processor becomes idle, and that is known as a memory bottleneck. And solving that bottleneck has become one of the most important challenges in modern AI hardware. The technology designed to solve this problem is called high bandwidth memory, or HBM. Most computers today use memory known as DRAM, which stands for Dynamic Random Access Memory. It stores the data that processors actively use while running software. And in traditional computer architecture, DRAM chips sit some distance away from the processor on the motherboard. Data travels between the processor and the memory through electrical connections on the circuit board. For many workloads, this sounds perfectly well and it works well. But AI workloads are different. Modern neural networks contain billions or trillions of parameters. Training these models requires constantly reading and writing huge blocks of data. The speed at which memory can deliver data to the processor is called memory bandwidth. And for AI workloads, bandwidth is often more important than the raw compute even. A GPU might be capable of performing trillions of calculations per second, but if memory cannot feed it the data quick enough, much of that compute capacity goes unused. This problem forced engineers to rethink how memory is built. High bandwidth memory, or HBM, is a completely different approach to memory design. Instead of placing memory chips far away from the processor, HBM stacks multiple layers of memory vertically on top of each other. These layers are connected using microscopic vertical wires called through-silicon vias, or TSV. Think of TSV as tiny tunnels drilled directly through the silicon. They allow signals to travel vertically between layers of memory. This stacked structure allows many memory chips to operate together as a single unit. But the most important innovation is where the memory sits. HBM is placed extremely close to the processor, often just millimeters away. Both the GPU and HBM stacks are mounted on a special silicon base that is known as the interposer. This structure dramatically shortens the distance that the data must travel. Shorter distances mean faster communication, much higher bandwidth. The result is memory capable of delivering several times more data per second than traditional DRAM. AI models process enormous matrices containing billions of values. During training, these matrices must be constantly loaded, multiplied, updated, and written back. That means that the GPU must continuously receive data from memory. HBM allows this by providing extremely wide communication channels between the processor and memory. Instead of narrow data pathways used in conventional memory, HBM uses very wide buses capable of transferring massive volumes of data simultaneously. As of 2026, we are already seeing the first HBM4 stacks, which double the interface width again. As a result, speeds are now pushing towards 4 terabytes per second. To understand how extreme this is, consider that a typical laptop memory system might deliver tens of gigabytes per second. HBM delivers orders of magnitude more bandwidth. And this is why the latest AI accelerators, such as NVIDIA's upcoming Vera Rubin or current Blackwell, rely heavily on HBM. Without it, these processors could not operate anywhere near their full potential. But HBM is far more difficult to manufacture than traditional DRAM memory. The stacked design requires extremely precise engineering and advanced semiconductor processes that push the limits of physics. Today, only 3 companies in the world are capable of producing HBM at scale: SK Hynix, Samsung, and Micron. For the last few years, SK Hynix has been the undisputed leader. They were the first to perfect the mass reflow molded underfill process, which allowed them to stack layers more efficiently than anybody else. And that is what made them the primary supplier for NVIDIA's world-dominating Hopper design. But the competition is reaching a boiling point. Samsung has pivoted its entire semiconductor division to catch up, pouring billions into HBM4 development. Meanwhile, Micron, the American contender, has carved out a significant niche by offering extremely energy-efficient products, which is critical for data centers trying to lower their massive power bills. Demand for HBM has exploded so quickly that it has created a sold-out market, because each AI GPU requires multiple HBM stacks. The memory industry has shifted from a commodity business to a high-stakes bottleneck. In fact, in 2024 and 2025, we saw the industry hit a wall. GPU production wasn't just limited by how many processors NVIDIA could design, but by how many HBM stacks these 3 companies could physically churn out. And as we move into the era of next-gen platforms, such as NVIDIA's Rubin, the winner of the memory war will likely be whoever can master the transition to HBM4 first. Manufacturing HBM is not just about producing memory chips. It requires advanced semiconductor packaging technologies. Each memory stack must be carefully aligned, bonded, and connected to the processor through the silicon interposer. This process is complex and expensive. Even small manufacturing defects can cause an entire memory stack to fail. The difficulty of producing these systems means supply cannot increase overnight. And building new memory fabs takes years and billions of dollars. And as AI demand grows rapidly, memory manufacturers are racing to expand production. But for now, HBM remains one of the most constrained resources in the AI ecosystem. So far in the series, we have explored 2 critical components of AI infrastructure. First, the GPU, which performs the calculations. Second, high bandwidth memory, which feeds data to the processor. But these chips do not appear magically. They must be manufactured using some of the most advanced industrial facilities ever built. Facilities capable of producing transistors measured in billions of a meter. In the next episode, we will explore the factories that make modern AI chips possible, as well as the company that sits at the center of this manufacturing system. TSMC, the world's most advanced semiconductor foundry.